This section will provide a short introduction to hydraulic principles. The term hydraulics is derived from the Greek word hydros, which means water. It was in the 17th century hydraulics, as we know it, came into use. Based upon a principle discovered by the French scientist Pascal, it relates to the use of fluids in transmitting power. The International Organization for Standardization, ISO, has made standards for graphic symbols and circuit diagrams used for fluid power systems. ISO 1219. In this module, we will be using ISO symbols of hydraulic components. Système International d'Unité, SI, is the latest revision of a metric system created by French scientists in the 1790s. It replaces all previous metric systems. In this module, we will be using SI units such as Newton, N, meter, M, Pascal, PA. Hydraulic equipment can be found many places on board a vessel. It can be equipment such as steering gear, cargo and ballast valves, cranes, windlasses, mooring winches, hatches, jacks, loading ramps, watertight doors and pumps. It is very important that the crew knows how to operate and maintain the hydraulic equipment on board the vessel. Hydraulic advantages: automatic lubrication, high power-weight ratio, small components can handle large loads, simple design, flexibility, the same components can do a number of jobs, easy to control, precise motion control, speed control. A hydraulic motor can be controlled from 1 RPM to more than 1000 RPM. Instant stopping and reversibility, constant torque with variable speed, inbuilt safety, actuator can be stalled at full load, automatic braking, can be used in hazardous conditions. Pascal's law states that pressure applied to a confined fluid at any point is transmitted undiminished throughout the fluid in all directions and acts upon every part of the confining vessel at right angles to its interior surfaces and equally upon equal areas. To illustrate how Pascal's law works, you can see that 10 kilograms can support a 100 kilogram weight. This can be done because the forces are proportional to the piston areas. Movement depends on flow. If a hydraulic actuator is to move, the actuator must be supplied with fluid flow. If the cylinder is retracted, it can extend only if there is flow into port A. Rate of flow determines speed. The speed of the actuator depends upon the rate of flow. The faster the fluid flow to the actuator, the faster the actuator moves. Load determines pressure. Pressure is created when the flow of a fluid is resisted. The resistance may come from a load on an actuator or a restriction in the piping. Click on the hotspots. Pressure as a result of constant load. Here you can see an example of pressure as a result of constant load on an actuator. The pump delivers 10 litres per minute, and the load is 8,000 newtons. The area of the piston is 0.001 square meters. This will give a pressure of 8,000 kilopascals. Pressure equals force divided by area. The pressure will remain the same even if oil starts to leak past the piston in the actuator. The pressure will remain the same until there is an imbalance between the flow produced by the pump and the amount of flow being leaked past the piston. Pressure as a result of variable load. Here you can see an example of pressure as a result of variable load. The pump is connected to a pressure relief valve set at 100 megapascals and to a throttle valve. If the throttle valve is open, the oil from the pump flows unrestricted and there is no reading on the pressure gauge. If the valve is gradually closed, it will resist flow and pressure will build up. As the valve is restricted, the pressure will build up, and when the pressure reaches the set point of the pressure relief valve, it will open. Pressure will now remain at 100 megapascals. Further closing of the valve will result in less oil passing through the valve, and more passing through the relief valve. Loads in series. When resistances to flow are consecutive, the pressures accumulate. The pressure gauges indicate pressure required to overcome each load, plus back pressure from the load downstream. The pressure at the pump is the sum of pressures required to open individual loads. A hydraulic system has three areas of importance: the pressure within the system, the direction of flow, the flow rate of the oil. There are four basic components to any system: tank reservoir, pump, directional control valve, actuator. Extra components are added to the system for safety reasons and for fine-tuning of the system. On any hydraulic drawing, each of the system components is represented and identified by a symbol. These symbols are described in ISO 1219. The use of these symbols is not mandatory, but as a general rule the standards are followed. However, from time to time a non-standard symbol may be encountered. We will now show you a basic hydraulic system. The actuator and direction control valve are always shown in the dormant or non-activated position. Activate the lever on the direction control valve to move the actuator.